This is the January 2013 P1 section from the Core 1 exam. So the first question is about waves, and it tells us that we've got a loudspeaker with a frequency of 80 Hz, and it asks us what does 80 Hz mean. Now frequency is the number of waves per second, so the 80 Hz means that there are 80 waves per second. That is what frequency represents, so that's 1 mark. That question has been on the exam the last couple of years running about what is frequency, and people consistently get it wrong, so make sure you understand that frequency is the number of waves per second. Second question, we've got to look at a diagram of a wave, and it says what is the wavelength, so we've simply got to read it off. Now the wavelength, remember, is, you can do this two ways. You can either just remember that a wavelength is, or one wave is up, down and back again. So you can see from that it is 12, so the distance from the start to the end there is 12. The other way of remembering it is the distance between two peaks, and if you measure that again you'll see that is 15 there, 3 there, so again it's 12. The answer is 12 centimeters. Next question, the speed of the wave is 20 centimeters per second. Calculate the frequency. So to do this, we know that the speed is 20. We know that the wavelength, lambda, is 12 centimeters. And we need to calculate the frequency. So we look at our list of equations at the front of that book, and we spot that the equation for wave speed is equal to wavelength times frequency. Now because our wavelength is in centimeters, but our speed is also in centimeters per second, I don't need to do a unit conversion. What I do need to do is rearrange this equation. So I need to get frequency on its own, so I do wave speed divided by wavelength will be equal to the frequency. So I do 20 divided by 12, which gives me an answer of 1.67 Hertz. So that's the equivalent of 1.67 waves per second. Okay, the next question is again another calculation. This is about heat. So it tells us we've got a radiator, and that the water enters the radiator at 65 degrees and leaves at 63, and that the radiator gives out 2000 joules of heat energy per second. It tells us the specific heat capacity of water as 4200, and it tells us to calculate the mass of water flowing through the radiator each second. So I write all my information out as my step number 1, and then select my equation, which is energy is equal to mass times specific heat capacity times change in temperature, and I've got to rearrange that to give me mass, so I've got to get it on its own. So I divide it by specific heat capacity and I divide it by change in temperature. So mass is equal to the energy divided by specific heat capacity times the change in temperature. So when I put my numbers in, it's going to be 2000 divided by 4200, and then the change in temperature, remember, is the difference between 65 and 63, which is only 2. And then when I put my numbers in for that and do it in my calculator, I get an answer of 0.24 kilograms. Okay, and that will give me 3 marks for that question. 1 mark for this equation, 1 mark for rearranging correctly and putting my numbers in, and 1 mark for my answer. Next question is Laura thinks about an identical radiator, but the difference is now she's using oil. She's told us that oil has a lower specific heat capacity. How can the radiator give out the same amount of energy? So all we've got to do with this is think about the equation. So energy is equal to mass specific heat capacity times change in temperature. Now we've been told that the specific heat capacity is lower, which would reduce the energy transfer if everything else stayed the same. Now we can assume that the mass of oil that's going to fill the radiator will be the same, so the answer focuses on this part here. So we have to say that the oil entering would either need to be at a higher temperature, so for example 67 degrees, or that it's flowing through the radiator faster, so that it transfers the heat, it transfers more heat energy, or that you could simply say that the temperature difference is greater between entering and leaving the radiator. 1 mark. The next question is our 6-mark question, and again this is around the topic of heat, and it's about reducing energy loss. So Oliver knows that the U value of the insulation in the ceiling is a measure of the rate of energy loss. He knows that the smaller this number, the better insulator it is. Now the question, he says that Oliver thinks doubling the thickness of insulation will halve his heating bills. Describe how the loft insulation reduces energy loss. Now that, describe how the insulation reduces energy loss is a key bit, and then suggest reasons why Oliver's heating bills are not halved. So the main bit of this is explaining how insulation works. So you need to remember that there are 3 types of thermal transfer. You've got conduction, which typically happens most through solids. You've got convection, which happens in liquids, and then the third one, which doesn't play as much of a part with insulation in loft insulation, the other one is radiation. And basically you get all your marks in this question by describing these and describing how heat loss reduces them. So the level 1 things that you were expected to know is that the insulation will reduce heat loss by conduction and or convection and or radiation. So if you mention any of those, you should get some marks. Now the insulation, one key thing that it does is it traps air. Okay, that's a key idea, and the reason for that is that air is a good insulator. So when we're talking about any insulator, all we mean is it's a material that reduces energy transfer, and air does that particularly very well. Now that's a sort of low-level answer for conduction, convection, radiation. You can then go on to explain a little bit more. So the trapped air in the insulator specifically reduces heat loss by convection, because the air is not free to move around, and so it doesn't lose heat so well in this way. Air is a poor conductor, so it doesn't tend to lose it very much by conduction. Now when heat is lost by conduction, the way it happens is that the particles transfer their kinetic energy. So if I've got a row of particles in a solid, as I start to heat them up, they start to vibrate more forwards and backwards, and those vibrations pass kinetic energy down through the other particles. So that's an explanation of conduction. If you're talking about convection, that's a little bit different, because now what happens is, because we're talking about air or liquids with convection, it's about density that's important. So in convection what happens is we have, as the air gets heated up, it becomes less dense, and the less dense material rises. It will then cool down when it reaches like a colder region, and then that cycle will be set up and it will keep repeating this, and this is what we call a convection current. So you need to know for convection that less dense material rises, and so effectively that's why heat rises. The radiation is very minimal with this, but you can mention the fact that because the insulation is going to be a lower temperature than it would be otherwise, then that's going to reduce radiation. The second part of the question, reasons why Oliver's heating bills are not halved. Well, what you would need to do for this is you look at examples on the table. You can see the insulation's been doubled here, but you can see that hasn't been halved. So you can give quotes from the table to support that. The other key thing is to mention that heat is going to be lost not just from the ceiling, it's also going to be lost from other places in the home. So you could suggest those, so for example through the walls, and you would need cavity wall insulation for that. You can get drafts through underneath the bottom of a door. You can also lose it through the windows, so it would be important to have double glazing. So you can mention other places, and you can clearly see that again, if I double it, once again the energy bills aren't halved, so it's clear to see that from the table. Okay, so now we focus more on the sort of back half of P1 on the waves part. So this is about part of the electromagnetic spectrum, specifically infrared. And one of the uses of infrared is as a remote control. Now it says the signal from the remote control can change the channel on a television. Explain how. So this question is actually about digital signals. So you've got 1 mark for identifying the fact that a digital signal is used, and a digital signal is just one that's either on or off. Okay, so it's either a 1 or a 0, it's on or off. So a digital signal on a graph would look like this. Okay, it's only got 2 values, on or off, as opposed to an analog signal that's variable and continuously changing. So it's a digital signal, and the digital signal contains a code, so it's coded, and that code relates to a specific channel function. Okay, so those are the 2 marks that you'd put for that. The next question is about cooking with food, and it's comparing microwaves and conventional ovens. So it says, explain how potato is cooked in both ovens. So effectively the question is asking, how do these 2 objects cook food? But then you've got to also explain why microwaves cook the potato quicker. So when you're talking about microwaves, you need to recognise that microwaves will penetrate into the potato, and the microwaves will be absorbed by the fat and water molecules in the potato. That's what absorbs it. So it increases their kinetic energy. Now, other key things about a microwave is that the microwaves will be reflected off the walls on the inside, so they'll be reflected. The walls don't get hot, and the walls don't absorb the energy, so all the energy is being transferred to the fat and water molecules. Now, that's only going to be absorbed by the surface. Okay, it's only going to penetrate about 1 centimetre into the potato. So it's going to get to the centre then by conduction and convection. Okay, so the same kind of heat transfer that we talked about in the previous question. Now, a conventional oven is slightly different. This doesn't cook with microwaves, this cooks with infrared. So the infrared will only be absorbed by the surface of the material. It won't penetrate in that 1 centimetre. And so, again, it's going to be transferred to the centre by conduction and convection the same way, but it will take longer because the molecules aren't receiving their energy directly. So it will take longer, and that's the reason the microwave cooks the food quicker. This question is about light, and it says complete the path of light in Mary's second experiment. Now from this you can see that the angle that the light comes in at is the same as the angle it comes out at. So I haven't got a straight ruler function with this, but you should use a ruler to do this. But it will deflect off at 45 degrees, so it will come down to here. You'd get 1 mark for that, and then again as a straight line it should come up there, and you should complete your diagram just by adding arrows just to show the path like that. The last section then is on earthquake waves and UV radiation. So this question is quite straightforward. It's just asking about your knowledge of earthquake waves, which are S waves and P waves. Now if you remember that S waves are transverse waves, if you think of the S being part of the transverse, then that gives you the first one. So P waves are longitudinal, S waves are transverse. Now P waves, the P stands for primary, and that's because they arrive first. So P waves are faster than S waves, which means that those next two statements are incorrect. And P waves, they can travel through all parts of the Earth because they're longitudinal. S waves can't. They can't travel through liquids. They can't travel through the outer core. Next question is on UV radiation. So you've got to identify the lowest level of sun protection. To do this, you look at the minimum time to stay in the sun, which is 20. If you times that by an SPF factor, so for example 15, that means that I can stay in the sun for 300 minutes, which if I divide by 60, then gives me 5 hours. So the minimum one that I could use would be 15. The last question is suggest why people with darker skin have a lower risk of developing skin cancer. And the reason for that is that if you've got a darker skin colour, then you've got more melanin in your skin, which absorbs the radiation. So any reference to absorbing radiation is 1 mark. Or you could have mentioned anything that suggests that the UV radiation doesn't reach your underlying body tissue, so the tissue underneath your skin. Or you could have just mentioned that there's more melanin or more pigmentation in the skin, and that absorbs more UV radiation.